Egunon, Ongitori in el norte de Spain. Welcome to the last Quantum Center colloquium of this year. It's a great honor to have Professor Schneble, Dominik Schneble, here from Stony Brook University in the United States. He will talk about simulating waveguide QED with atomic matter waves. Dominik got his PhD in Konstanz, University of Konstanz in Germany. His master's before actually in the US, in the University of Massachusetts at Dartmouth. And after the PhD, he went again back to the US, to Boston, to the MIT, Harvard, cold atoms up, I think, and Wolfgang Ketterle. After which he quickly became professor at Stony Brook, working on experiments with cold atoms, and that is what he will tell us about today in this colloquium. So, Dominik, the floor is yours.
Yeah, thank you very much for the kind introduction. Thank you for coming to this colloquium. It's always a great pleasure for me to come to Bilbao. Last time I remember I gave a talk in the Department of Physics in a much smaller room. And so it's really nice to see how things have been growing and what a great center you have here for quantum science. So, yeah, I want to tell you about the experiments. I'm an experimentalist that we have been doing on quantum simulations of waveguide QED with atomic matter waves. So these are three things in the title already that I think I should explain. So I will spend a little bit of time on explaining what the system is all about and then tell you about what we actually have been simulating. Okay, so just to set the stage. So we're talking here about quantum simulation, and there are two different kinds of quantum simulations. One is digital and the other one is analog. So if you have a quantum computer, you can run quantum simulations on that computer simply by solving the equation of motion and evolving calculating the time evolution of the Hamiltonian. If the Hamiltonian is well behaved, you can break this time evolution down into a sequence of local gates that you can run on a quantum computer in small time steps. So this is a digital way to do simulation. Typically, if you have a complicated system and you want to follow its evolution, you need a very large number of such gates. And there's a little error attached to every operation, which means that you have to spend lots of quality time on error correction protocols in order to get some useful results. And so that's a limitation that you have in these systems, but it's certainly an increasingly popular way to do quantum simulation with all these platforms that you see down there. So the other simulation that you can do is analog, meaning that if you have a quantum system here, as before, instead of encoding the evolution into a sequence of quantum gates, you can just build another system that kind of looks like the system that you want to study, that has a Hamiltonian that looks kind of like the Hamiltonian that describes this system. And, oops, it's a little bit, sorry, the colors are not so good here. So if you have a correspondence between the system and the Hamiltonian, then you can just prepare your simulator in an initial state, follow its evolution experimentally, and then read out the result. And from the result, you can then learn something about how the system itself would behave without having to actually prepare the system. So you can learn sort of the evolution of the system by looking at the simulator. That's analog, simply because it's an analog kind of way to do this. But it's also analog in the sense that you have knobs that you can turn, because, I mean, the system that you prepare is ideally better controllable than the system that you want to study. Otherwise, there would be no reason to prepare your simulator. And so, in particular, you can control the parameters that determine the system. So these are parameters of the Hamiltonian, and you can also sort of adjust everything in a way that allows you to ask very well-defined questions about what's going to happen under which condition. And based on that knowledge, you then learn about what the Hamiltonian actually does. Okay, so in our case, we have a quite particular system that we want to study, and also our system is quite particular. This is something that is kind of common to all analog quantum simulators. They are not universal, or at least most of them. They are not really universal in the sense that you can do anything on them, but because you model them on this target system that you want to study, the system itself is quite special. Yeah. And so what we study here is a field, and I'm going to tell you about this. It's called waveguide QED. So these are quantum emitters, which are coupled very strongly to channels in which photons can travel. And by putting several quantum emitters in contact with that channel, the quantum emitters can talk to each other through the photonic channel. And actually, when you look at these systems that form the basis for the IBM quantum computers, for example, these are they work in a microwave domain. These are transmon qubits, meaning quantum emitters that are coupled to each other through some microwave channels. And so in some sense, what we want to study here is the physics that's happening in those platforms. That's one thing, is a more technical kind of perspective, but there's more fundamental questions, like what does it actually mean to couple a quantum emitter to vacuum, for example. Yeah. And so this is what we can study here. Okay, and so the Hamiltonian, I'm going to explain it, is the Hamiltonian that describes the interaction of a two-level system characterized by excited state and ground state with photonic modes, which are here represented with these creation operators B. Yeah? And so the photons, they are characterized by momentum. And if you have a continuum, like in vacuum, you have all kinds of momenta in here. And so you have to sort of sum up over all the momenta. And then so if you think about this process, what's happening here is that you go from the excited state to the ground state. And as you do this, you create a photon that's flying away. And you have the reverse process here also. Yeah? So this is the Hamiltonian that describes these systems, and it also describes our system just in a different way. So what is it that we are doing? So we create an emitter, two-level system, which emits a quote-unquote photon, except it's not a photon that comes out, but it's a particle that comes out, a massive particle. This particle is actually an atom itself. And so, but it follows the same physics, yeah? And the advantage is that we can control the parameters freely. For example, we can control the energy of the emitter freely. We can control the coupling to the vacuum freely. And we can control to which modes we couple very precisely. And so there are none of the problems that usually plague these systems, which give rise to decoherence, which is losses of the photon into unwanted modes that are not part of the system that you really want to study. Meaning the photon gets lost out of the waveguide somewhere else. So that's not happening in our case. Of course, I should say, there's a big drawback in our system, which is it's basically just a simulator. Yeah? So you cannot really use this to now build a system that can perform computations in a competitive way, but it's more there to sort of study fundamental effects and see what's happening as you go into novel regimes. Okay, so 10 years ago, I would have called, 20 years ago, I would have called this is our BSC machine. It makes Bose-Einstein condensates as a starting point. In this other new framework, this is our analog quantum simulator. Yeah. And we have a Hamiltonian inside that's encoded somewhere here. Yeah. Yeah, it's based on atomic physics. And so, in some sense, what we're doing here is the same as was done, that's 80 years ago, in analog simulators of, like, say, airplanes, in terms of that one sort of maps the behavior of an airplane into some analog circuits, and it has control knobs. In our case, it looks very similar. The simulator is here in another room. We sit here in front of the control knobs and just measure and prepare the system and then measure it and then learn from that. Okay, so before I tell you what we actually simulate, let me just tell you a little bit about what light-matter actions are, light-matter interactions are, and a little bit about the history. So we are considering a two-level system: excited state, ground state, transitions between the states, and the emission or absorption of photons. That's actually something which was already discussed by Einstein in 1917 in his famous paper, where he determines the A and B coefficients and considers this a gas of such atoms in equilibrium with the thermal distribution of photons. But that wasn't really a quantum description, it was just basically a thermodynamic or statistical mechanical description. The first physicist who looked at this was Dirac, and that's actually in a paper written in 1927, around the same time that he analyzed the hydrogen atom. And in this paper here he says, well, so far nothing has been done on quantum electrodynamics, meaning that the electric field has not been quantized yet. There are no photons there yet. Should say in 1924, the concept of photons was already well advanced, so Bose-Einstein statistic was already invented, and so he solved this problem in terms of what it means for the interaction of light and matter. And so in this paper, he actually did quite a few things. He invented perturbation theory, saying that there's a Hamiltonian there that describes the atom, there's a Hamiltonian that describes the field, and then there's an interaction, and this is weak. He quantizes the field, and out comes something that in today's language is almost not understandable. But if you look at this paper long enough, you find there that there is something like an n+1, yeah? Which is sort of stimulated piece and spontaneous piece, and then there's an n here which corresponds to absorption. So this is absorption, stimulated emission, and spontaneous emission. And in today's language, you can rewrite this Hamiltonian in this way. Yeah? So you have the atom, so ground state energy is set to 0, so you have omega Eg if you're up there. Here is the energy of the electromagnetic field, summing up over all the modes, and then here's the interaction. And so what characterizes this interaction? I mean, you see here has the same terms. Yeah? You should go from E to G, you produce something, now it's called A, not B, I apologize. Yeah? And then there's a coupling strength in the front. And what is this coupling strength? It is the dipole coupling between the transition dipole, DEG, yeah, and a vacuum field. And this is basically 0 point, if you have a zero, you quantize the electromagnetic field, you have a 0 point energy, correspondingly you have a 0 point electric field. That's of every mode, yeah? And then that couples with the dipole moment. So that is what makes this happen. Yeah? So coupling of the dipole to the vacuum. Okay, so Dirac, being very high-level theorist, did not actually use this to calculate the decay behavior or line width, so just that it can be done. And so there was a PhD student at the time who just started out, Victor Weisskopf, who started working on this problem. And I think he was working with Max Born in Göttingen. There's an N missing for some reason. And so at some point, Wigner visited, and so they started talking about this problem, and then Weizkopf knew how to solve it. And they say here, we don't solve it in the usual way. Now, it's not clear what the usual way was, but I think it's using Fermat's golden rule, essentially. And so what they did is they tried to solve it exactly. Yeah? And so you have this Hamiltonian, and you just solve Schrödinger's equation. In order to do this, you have to make an ansatz. And so the ansatz for the wave function here is that, well, either you're in an excited state, and you have no photon, or you're in the ground state, and you have one photon, and the photon is in some mode. Okay, and you have to sum up over all those modes. And you have coefficients here that tell you what's the amplitude to be in each mode. And here is the amplitude to be excited. Yeah? And so you take this wave equation, this wave function ansatz, put in wave equation, solve it, and you can sort of eliminate the b's, and you get an equation of motion for the amplitude to be in excited state. Now, this actually, when you do this, depends on the history, yeah? So of all previous times. But they knew in this paper, so they didn't solve this actually, they knew it should be exponential decay. That's what one observes. So how can you make this exponential decay? Well, you pull this A out of the time evolution, just put in front. Now you have a simple exponential, and you can calculate what the line width is. So this is known as the Wigner-Weizkopf approximation or the Markov approximation, and so it basically works if this time evolution of A, so the change of A is so slow that it's basically constant on the time scale of all those oscillations. Yeah? So very fast oscillations on the order of the optical frequency, and we have a slow decay, and so it's quasi-adiabatic, can just pull it out. Now, they made a few tweaks here. For example, when you now want to calculate this integral, you can probably kick out the t, just replace it with infinity, so it's going to decay. And the error you're making is very small if you integrate out to infinity. Also here, the sum over the photon momenta you can replace by an integral over the photon energies. And physically speaking, there are no negative energy photons, and so you can just, integrate from 0 to infinity. However, you're not making a big mistake if you also include the negative energies. And now this is simple delta function that you can calculate, and you get out the decay rate. And now if you compare this to Fermat's golden rule, you actually see that it's pretty much what you expect. It's the coupling of the dipole moment to the resonant zero-point field, squared, so this is the matrix element, and then you have a density of states out there, which gives you that strength. Now, already in that paper, they realized that actually, if we are precise, if you're not doing this here negative energies, this changes, there's going to be an imaginary part there. And so there's a principal value that you have to take into account. And so that reproduces actually something, or predicts something, it's called the lamp shift, which is the coherent part of the interaction. Yeah, so that's basically shifting the energy, the distance between the levels. So yeah, so they predicted this, and this was then solved more precisely later, after this Shelter Island conference in 1946, or 47, where Lamb presented the first credible measurements of this. And there were measurements before, but he had really this down to like 1 gigahertz for the transition in hydrogen. Okay, so now, so far so good. Now one can ask, when does this approximation actually work? It certainly works if you have a very narrow transition. Yeah? I mean, think about optical transition. It's maybe 10 to the 15 hertz, and then you have a line width of maybe megahertz or 10 megahertz. And so it's basically very, very sharp transition based on that very far away here from the ground level, yeah? So from the zero energy. And so if you have a sharp transition, this works. However, if you now have full tunability of the parameters, you can think of other scenarios. You can think of making this coupling so strong that the decay becomes very fast and the line width goes up. Yeah? And so at some point, the line will sort of feel the edge of the continuum. So that's violating this assumption. You can do other tricks, like in this waveguide QED. You can put bands, optical bands. So these are regions in which no photon can propagate. And so we have forbidden regions, and so that certainly doesn't correspond to this anymore. Yeah. Or you could go into a scenario where you don't have a continuum of modes, but you just have a single one. And then certainly also this doesn't give you exponential decay. And actually this scenario here is very well known. It's cavity QED. So in this case you get just Rabi oscillations between the atom being excited and the cavity being excited, so photon in and out. This is the basically waveguide QED or photonic bandgap materials that will live in this regime. And then here is a strong coupling limit. Okay, and so in our system, because everything is tunable, we can sort of explore all of that. And so that's kind of nice. Okay, so now the question is, how can you build this system? So what do you need? So the idea is very simple. If you look at the conventional system, you have an emitter, ground and excited state, and you have a coupling to the vacuum, and as a result of the coupling, you go from the excited state to the ground state, and the photon comes out. Okay, and so this photon will have a wavelength related to momentum, and it has and the momentum is related to the energy of the photon, which is a linear relation in free space. Now, in our case, what we do is we just make an emitter, so a two-level system, and we say if the, in this case, particle or the atom is inside, we call this excited, same way that if you think about an emitter, it's a container, basically for photon. I mean, it's wrong to think about it this way, but you could sort of model it in a way that the container is full or empty. So either the photon is inside or it comes out. And so here we have a container where we have an excitation, which is an atom. We have vacuum coupling, the atom comes out, and the container is empty. And we call it, label it as being in the ground state. Now the difference here is that this excitation here, apart from well, electromagnetic energy, maybe it doesn't have a mass, yeah? But an atom, if this is an atom here, it has a rest mass, which is huge. But yeah, the rest mass comes out, and so you have, at least for low energies as we have it, you have kinetic energy and rest energy. And so we can just kick out the rest energy. It leaves the considerations. We're just left with the kinetic energy. And if you take the kinetic energy, yes, we have now a wavelength. We call this now de Broglie wavelength. There's momentum, and the momentum is related to the energy. E is equal to 1/2 mc² squared in this way. Yeah. So it's a different dispersion relation than we have for the photons. However, if you are close to a band gap, I'm going to tell you that in a second, you have your dispersion relation for a photon in a photonic band gap material is quadratic, yeah? And so you have the same dispersion relation here and as you have here. So there's a direct correspondence, yeah? And so on that level, these systems are equivalent. Okay, so what do you need? Well, you need an atom, you need internal states. These are hyperfine states separated by a few gigahertz. It's a rubidium atom. So we take a single atom here, at least we consider a single atom, two states. We couple them through microwave radiation. So it's a classical field. Yeah? So it's not like microwave photons. It is, but it's so strong that you don't have to think about photons. Also what we have is now an optical potential. So this is a potential in which you put the atom. Yeah? And it has a very special properties in the sense that if you're down here in red, you see the potential. So it's essentially just a standing wave of light in front of a mirror. Whereas if you're in blue, you don't see it. And it's possible to make such potentials. And then, after we prepare the system and let it evolve, we analyze everything. So how do we do that? Well, we can separate out blue from red by passing the atom through an inhomogeneous magnetic field. So these have different magnetic moments, these two states, and so they fly off in different directions. So we can separate red from blue. And then also, because we are flying, if we have some motion in the red or in the blue, we can track it out. Yeah, so it's a time of flight technique. Okay, and so these are standard tools, yeah, that every BSc lab more or less has. Okay, so we did this here in this paper a few years ago. Just to explain again, so if you have two levels, and you couple them with some classical radiation, you get Rabi oscillations between red and blue. And so this is described by this Hamiltonian. Yeah. So you go from red to blue, and you have a strength, coupling strength is the Rabi frequency. Okay, and now you apply this external potential. So red now sits in a well, blue does not. Yeah. So red is fixed, blue is not. However, blue is free to move. Yeah, so there are states there that blue can occupy, and those states are motional states, just free motion, plane wave states. And so now if you couple, let's say you are in red and you couple through this coupling here to blue, there is one state here in this continuum that's going to be at the same energy. And so you can resonantly go out, yeah? So we say, okay, I get Rabi oscillations between here and here, yeah? But what kind of Rabi oscillation is this? You leave the well and you move away, right? And then sort of come back in. But it's actually a whole continuum, and so there are other states that are not quite resonant. And so that's what gives you this Hamiltonian that looks just like the Dirac Hamiltonian, except if you now compare, before we had this coupling strength, which was D dot E, yeah, here. You don't see this here. What you have here is this piece, which is the Rabi frequency from the microwave coupling. And then there's some overlap between this wave function and this wave function, which we could call the Frank-Condon overlap. But it basically tells you how strongly you couple out to those states. But yeah, these omega, the strength is tunable. We can just change the strength of the microwave coupling here, yeah? And we can change the height here above the ground by changing, I didn't explain this here, but there's a detuning of the microwave. So it tells you how far away you are from the resonance. We can change that as well. So it's all tunable here, and so we can explore the whole range of parameters. Okay, so now here is a simple experiment, spontaneous decay. Yeah, so prepare your system in an excited state, let the atoms decay, and you get a spontaneous decay. Now you can go to strong coupling by making a coupling really strong or making the emission energy really low, and in the extreme case you have just that. And so what you see then is that this exponential decay turns into an oscillatory behavior. So that's not Markovian anymore. Weisskopf-Wigner approximation is not valid, or simply what happens here is that radiation comes out and goes back in. So it gets sucked back in and does this a few times. Okay, so yeah, one sees already this was some model that we made for a single emitter, so that doesn't quite fit. And the reason for this is that the emitter is going to be an optical lattice, so there's many of them. And so I'm going to tell you about it in a second, what this means. Now, the emission, we can look at what comes out. Yeah? And so when you do this time of flight, you see basically two blobs. So there's atoms which fly out this direction, atoms which fly out this direction. You just let them fly and then look at where they are, you see two blobs. So you see one here, and we see one there. And now the energy of this depends on the excitation energy here. Yeah? And so if you scan the excitation energy, you see a parabola, which is just your dispersion relation. So that's just what's expected here. The dashed line is just energy conservation, and have a little bit of a line width there. Okay, so one thing is you also see something at negative energy. So what we can do in our system is quite weird. We can pull the excited state below the ground state. And then when you emit, it means that, yeah, so here, when you emit, you go up in energy. And then what comes out has to have negative energy. And yeah, so it's the same as in the photonic bandgap material. I'm going to tell you about this. So if you have negative energy, yeah, this means that the momentum is imaginary. And that's what is an evanescent wave. Yeah, so things kind of ooze out, the radiation oozes out from the emitter, but cannot quite travel away because there's negative energy. But it's still kind of there. Yeah? And so this is so-called atom-photon bound state in optics. So it's basically a cloud of excitations, photons, that surrounds this emitter but cannot escape. Okay, yeah, so basically this is an artistic representation of this. Okay, yeah, and so when you decay, let's say you are at negative energy, you turn on the vacuum coupling, what you see is a little bit of an oscillation. And so this is stuff, it's kind of transient, so radiation gets emitted, but then most of it stays behind and forms this cloud, or this bound state. Okay, so back to now waveguide QED. So this is the dispersion relation of a photon. If you put this into a photonic crystal, if you put radiation into photonic crystal, so it's just high refractive index low, high, low, high, low. Yeah, it's basically a Bragg structure. You form photonic bands, and you can be now in the continuum here. In which case you can propagate, but you get these kind of non-Markovian oscillations, in principle at least. Yeah. Or you can be in the forbidden region, in which case you are below the continuum, I mean below this continuum, or above this continuum, it doesn't matter. Yeah. And now you form these atom-photon bound states. And so what's nice about those states is actually they can be quite long ranged, and they can sort of reach another emitter. And now what can happen is that the photon virtually comes out here, is here, and this thing is in the ground state and can reabsorb the photon. Yeah? And so in this case, this emitter here loses the excitation, and this emitter gains it. And so this is a coherent exchange, coherent spin exchange between the two emitters. It's actually equivalent to resonant dipole-dipole interaction in between two atoms. Yeah. So there's no dissipation involved, it's all coherent. Okay, so here are systems that form waveguide QED. So you can have atoms, for example, close to a fiber. Photon goes into the fiber, propagates, and then couples those atoms. You can make this fiber, you can structure it to make it basically a photonic crystal waveguide. This is called the alligator waveguide here. Now you form these bands. Yeah? Also here you can do this in 2D. This is an example with quantum dots and a photonic crystal wave coupled to photonic crystal waveguide. You can use vacancy centers, put them in photonic crystals. So there's all kinds of platforms in the optical domain, but there's also the same physics in circuit QED where you have transport qubits coupled to microwave guides, coupled to other transport qubits. And so if you have a regular array of them, now you have a photonic crystal waveguide, and they have the quantum emitters coupled to them. Okay, so in our case, we simulate this, and now notice that we have an optical lattice. Yeah? So I told you about this red potential made by a standing wave of light, makes many, many wells. Yeah? So if you think about this, there's a whole bunch of them aligned. And some of them, or one of them will have an atom in it, the other ones don't. So they are basically empty emitters or ground state emitters. That provides some coupling between them. And so I want to tell you about, well, time is already getting short, about an experiment that we did very recently, which is sub and superradiance in this system. So if you have a single atom, it decays exponentially. But let's suppose you have the situation that you have an excited atom and you put a ground state atom next to it. What happens now? So, as a famous physicist, Robert Dicke, 70 years ago, he looked at this and he predicted that it would fall to 1/2, decay to 1/2. So first you decay faster, yeah, or on that scale it's the same, start out same, and then you end up at 1/2. Why is that? It's simply because this situation you can rewrite into a sum of a symmetric piece and an antisymmetric piece. And the symmetric piece will decay at twice the rate, but the antisymmetric piece won't decay at all. Yeah. And so in other words, you can write this here as this configuration as this superposition of antisymmetric and symmetric, symmetric and antisymmetric, and the antisymmetric piece will survive. That's called subradiant or non-radiant, and this symmetric piece, which decays faster with twice the rate, is called superradiant. Okay, so if you now do this in a waveguide and the emitters are at some distance, it's a little bit different, but not so much. Yeah. So you have basically radiation that comes out here, radiation that comes out here. There's actually now a phase difference, simply because you have a distance here between them, so you need to take this into account. But if you do that, and you can control this phase here now, you can make it such that you get constructive interference and destructive interference. And in one case, if you get constructive interference between these radiations, you decay superradiantly. In the other case, you don't decay at all. Okay, so in general, these states will just be EG plus GE with some phase. Yeah? And so they're called timed decay states. It's a term from optics, simply because one usually excites them with a weak laser beam that comes and sort of hits the atoms at different times and then excites them with some chance. And so this is called a timed decay state. Now in our system, we can do this simply by starting out with a superfluid. What is a superfluid? It's a state of a quantum gas where each atom is smeared out over all the wells. Yeah. So before, we had a bunch of wells with a single well had an atom in it, but you can prepare a system also, an initial state where the atom is smeared out over all the wells. You don't know where it is. It's coherently smeared out. And you have many of them, but you can just focus on one. So this one atom here is smeared out coherently over all the wells. You don't know where it is. Yeah? And so that's basically a situation that looks very much like a time decay state or a symmetric state where you have excitation either here or here and then here in the ground state. Yeah? So ground, excited ground, and here ground excited, and so on. So don't worry about the fact that there's more than one atom in the quantum gas. It turns out there's actually all single atom physics. Okay, so just as a reference, we can start out with a thermal gas to make something like we had before, and you see this parabola. So that's a gas where you have no coherence, but you know exactly where the atom is. Yeah? And so you get basically the parabola from before. Now if you switch to a superfluid, where each atom is coherently smeared out, what you see is that this parabola turns into this. Yeah? And so now, I mean, what do we have here? This is the excitation energy. You see that there are certain excitation energies at which you get more than before, yeah? And others where you get less. So this would be super, and this would be subradiant. And yeah, so I mean, this all makes sense. It is exactly where you would expect it, with constructive and destructive interference. And now you can basically play around with this. So yeah, how do we do this? Here, Professor Modugno is an expert in Bloch oscillations in optical lattices. Yeah. So what you do is you just sort of apply a gradient for a while, which means that these wells, they have now different phases, or phases evolve, yeah, and you get a phase difference between the neighboring wells, and you can do this simply by turning off your trap for a while, leaving the lattice on, and letting gravity do its job. Yeah. And so this way you can imprint a phase gradient across the emitters. And so what you see as a function of this phase, there's a phase difference between neighboring wells, is that these blobs move. Yeah. And so you can make quite exotic things, do quite exotic things. For example, here now, at this energy, you emit to the right superradiantly, and you don't emit to the left at all. Yeah. Or if you think about it, here at 2, this was a subradiant case. If you prepare the phase correspondingly, well, it's actually, that we didn't use 2 here, but let's say at 1, yeah, you can get superradiance at a completely different energy if you sort of change the wavelengths, yeah, because all you need for superradiance is constructive interference. So if you have some phase difference between the emitters, but change the length of the wavelengths, you can still get constructive interference. And so you can tune between these different cases. Yeah, so here you have destructive interference now, and here you have constructive interference. Now all we did to go from superradiance to subradiance here was we changed the phase of the emitter. It's actually quite strange. Yeah. What does it mean to have a phase on an emitter? It's a quantum phase. You change it from being both up to up and down. Yeah. And so you can change the emission behavior by just controlling this quantum phase. So that's what we did if you just look at this line. Yeah. The same thing, of course, here. Okay. Now something also very interesting, I'm running out of time, is if you look at the decay behavior. How many minutes do I have? Like 5? Yeah. Okay, if you look at the decay behavior, this here is in gray is the behavior of a single emitter. Yeah. And so even if you have a superradiant case, you start out like that, yeah, like a single emitter, but then it gets faster. And so there's actually 2 time scales here. A slow decay for some time, and then a faster decay for some other time. So why is this? It's simply because when you turn on the vacuum coupling, which we do by turning on microwave, the radiation now leaves the emitter, but it's slow, yeah? So it needs some time to reach the neighbor, and only then does the neighbor know that there's a neighbor. And so that's a regime that has never been observed, simply because photons travel at the speed of light, and the system sizes are usually very small, and so you never see this effect. But in our case, we are 10 billion times slower than photons. The system size is comparable. Now we can track this behavior. And so you see a speed up here. Yeah? And actually, if you look at the momentum distribution, you see this, that yes, it's actually, and you do Fourier transform, you see that yes, it's actually when the radiation reaches the neighbor, that's when it starts to get faster. Okay, so there's a non-Markovian superradiance, which is kind of something that people have been looking for a long time, at least in theory, and so we were able to observe it here. You can also look at subradiance. So this would be a single emitter behavior. What you see now is that you don't decay anymore, but you see these oscillations. Yeah? And so these oscillations, why are they there? Because, again, you start out without seeing the neighbor. Now you're already down a little bit. Now you need to go back up. Yeah? And so that's why you get those, at least in very non-technical terms. Now you can analyze this system very carefully. One of my students did this, and you can sort of identify the underlying mechanisms, and it's essentially here a beat between two things. It's a beat between this bound state that I told you before about, yeah? So that radiation kind of cannot escape, simply because we are not completely above the continuum. And then there's something called the bound state in the continuum, which is a state that involves more than one emitter, where the radiation sits between the emitters. So the emitters here are in red, yeah. So these are is the on-site wave function, so it's a little bit blurry. But you see here that in between you have a maximum of the blue. Yeah. So in other words, radiation comes out of the emitter, and the next emitter acts as a mirror, and so neighboring emitters form basically a cavity, and the radiation is trapped in between. So that's known as a bound state in the continuum, and these two things beat against each other and make this dynamics. And you can see it here. That's sort of the time dynamics. And so actually we can measure this in the radiation. This is our measurement. This is the corresponding prediction from the calculation. And so you see it fits pretty well. So that we are confident that that's actually what's happening. Okay. Okay, so you can, just to be complete, you can go from superfluid to mod insulator. Now you have one atom per emitter, or one excitation per emitter, fully excited. Turn on the vacuum coupling, what do you get? So it's called decay ladder, so just for two atoms. Yeah. So if you have two excited atoms, the next step brings you down here. You don't know, if you have decay, you could go down here, or you could lose it here. So you have a symmetric combination again. And then if you do it again, now it's a symmetric combination that decays faster, yeah, and you go down to the full ground state. Okay, and so the main point is that you have something that's not coherent up here, and then the spontaneous emission creates a coherence. So where you don't know where you are in terms of the excitation, and then in the end you decay completely. So in a mod insulator, this is very simple. Yeah. Two poles excited, no coherence. You lose it here or you lose it here. And actually, because we are now not at the same position, but we are in an array, you pick up this phase when you have the decay, and then you decay completely. So there's so the decay induces a coherence, yeah, which is kind of a little bit counterintuitive, that there's spontaneous processes create coherences, but I mean that's the essence of superradiance in some sense. So yeah, so basically there's a paper by Dickey 10 years later where it says the memory of the direction of emission of the first photon is burned into the energy level structure of the radiating system. Yeah, and so this is the radiating system. That's the photon here. If you take it away, you still have that. Yeah. And so the photon has left an imprint in the form of this phase. Okay, so we look at the decay. It actually looks like a single emitter, which was a little bit disappointing, so no speed up, but we can explain this through kind of technical considerations. Anyway, we looked at the momentum distribution of the array, which is something we can do. No other system can do this, but we can sort of just analyze in the array of emitters, is there any coherence there? And what we found is a little bit of something. Yeah? So it's a sharpening here and a flattening there of the distribution. And if you subtract the two, you have some feature. And this feature might be the signature of this phase. Yeah? Now it's very hard to measure and hard to model, so we changed our system a little bit, and that shows you how flexible we are. So we have red and blue, yeah? But we can also have green, for example. Yeah? Turns out green also sees the lattice, yeah? And so we have a second state. Now green is not coupled to blue, so it does not decay. Yeah? But anyway, we can prepare a system, let's say in a superposition, we are in a superposition now of red and green. So we prepare our system in red, turn everything into a superposition of red and green, then turn on the vacuum coupling and have decay. However, green does not decay, only red does. So you see here, green stays the same as a function of the decay. However, green has this kind of weird feature in momentum distribution. So there's something going on to green, something's happening to green, even though green is not affected by the decay. So what is this? It's very simple to understand. You have a red-green superposition in each state. You can write this here as a superposition, or between those possibilities. And now red decays, yeah? Green does not, but when red decays, it imprints this phase. And this phase is now there, but the system that you have burnt your memory into isn't red, it's green. Yeah? And so it's the same kind of features as for the red before, just in the green. Green did not decay, but the imprint is still there. So we're able to sort of model this. This is a calculation here, yeah? So it fits pretty well, so we're confident that yes, this is this phase. Okay, so that's the summary here. So yeah, we prepare a system that simulates a waveguide QED. We access new parameter regimes. I mean, so far, this was now 6 years ago, that's these first measurements on this oscillatory decay. In the meantime, some quantum optical systems have also absorbed it, so, but we at least first ones to sort of show that this can be done. We can control the coherence in the emitters. We see superradiance, yeah, and we see basically that there's some, we didn't talk about this, but there's some effects of interactions also that sort of modify what we observe away from simple superradiance. Yeah, so he graduated now, had a very ambitious PhD student who, I mean, it's very hard to calculate many-body dynamics that's not Markovian. And so we said, okay, you calculated for a single excitation, check mark, you did that. Now you do 2 excitations. And so those excitations can either live in the waveguide or they can distribute themselves over the emitters, but the condition is you cannot have 2 excitations in an emitter. Yeah? It cannot be doubly excited. So there's all kinds of constraints. There's fermionic behavior up here and bosonic down here, but anyway, he was able to solve it and make some predictions for the dynamics. So you see here, this is Markovian decay, and here's some non-Markovian oscillations. We haven't observed them yet, but it's definitely something we can do. This calculation was done for coupling into a band, photonic band. We know already that we can couple the photonic bands by isolating one. Yeah, so this is, you see here, a photonic crystal analog. If you couple to a band, you can see that you're coupling to a band. So the conditions are fulfillable. And yeah, actually, we also already looked at some features, like when you're coupling very strongly, you get basically Rabi oscillations, you use cavity QED limit. If you couple weakly, you're very far away from the edges, you get exponential more or less decay. Yeah. So we can tune, this is a tunable system, and so we can essentially use it to study such superradiant, subradiant effects in these regimes as well. Okay, so just back to this. Yeah, so the question is, of course, always like, okay, you're simulating something. Are you a slave to what you're simulating, or are there new features that you can also get? And I think the new features that we have is that we can change the character of the radiation that comes out. It doesn't have to be bosons like photons are, but it could be fermions. Could either do this with fermionic atoms in a lattice, or you could make it that you're emitting into a very tightly confining tube, which is Tonks gas, so basically a fermionized situation, and then this becomes actually quite interesting in its own right. Okay, you can do other things, like I don't want to talk about it, no time, but we can sort of create what we call matter wave polaritons. These are now red atoms that can tunnel in this lattice, but which are dressed with these excitations, forming basically a bound state that can hop from side to side, and it has different properties. It moves differently at different speeds, has interactions that are different, so you can make some kind of strongly interacting gas of these polaritons. So we can just to say that our system not only can simulate waveguide QED, but it can also simulate condensed matter physics, where you have some coupling to radiation. Okay, so with this, I'm at the end of my talk, and just here acknowledging my team. This is not a snapshot in time, it's a time-integrated picture. So there's people who have long graduated, people who just graduated, but what I showed you, this work is basically integrated over all their contributions, and the super-radiant work, that most recent one, was done by Yongshin Kim. He's now a postdoc at Harvard, and Alfonso Lanuza, who is actually very close to here, is a postdoc at Burgos, University of Burgos, and mathematical physics group there. Okay, so thank you very much for your attention.
Thank you very much, Dominik. Very exciting talk, many results you showed. Next time you show also a movie, maybe how you actually realize these measurements. We have some time maybe for questions.
I have one simple one. One of the last slides you showed, you did have different regimes of G over omega. However, if you look at normal light-matter interactions, you always have that the G is limited, I don't know, times Thomas Rahe-Kuhn or whatever in TLS. And if I remember correctly, in this very Spanish matter wave proposal, because it's Inés de Vega, Diego Porras, and Ignacio Cirac.
Exactly, yeah. So that was the original proposal, yeah.
Inés is now in the private sector, Diego is in CSIC, and Ignacio, of course, still is in Garching.
Yeah.
And there, if I remember correctly, G is limited by the width of the wave function in the trapped state. So, is there any additional limitation like TRK or whatever?
So, actually, the fact that we have a Gaussian wave function in the wells is actually very convenient, because it chops off the coupling to the higher frequencies, and so otherwise you would have ultraviolet catastrophe, and this thing kind of nicely normalizes it out and actually makes things calculable in a very nice way. So what we can do is, of course, we can change the confinement in those wells to make the wave function more concentrated. Yeah. And so what you see when you do this is basically changing the line width. But I mean, definitely we can go from weak coupling to strong coupling in two ways, either by cranking up the vacuum coupling or by changing the excitation energy to be very small. So it's a strong coupling, but not ultra strong. Yeah, we cannot produce two atoms coming out, unfortunately, but it's still a single one.
So was when you showed this, when you had the chirality induced by the gradient by this phase gradient, essentially, and then you showed that you had degeneracy in superradiance in both chiralities at phi equals to pi. Yeah, in that region. To what extent isn't the degeneracy at phi equals to pi already this signal of this fermionization you were talking about?
So, I mean, fermionization we don't have in the system simply because we think about single particle, yeah? And so the fermionization that I was mentioning at the end is the fermionization in the tubes that happens once you have more than one atom. Yeah. But so that's actually something it's very interesting because it changes the whole dynamics. Yeah. So these measurements were all done with tubes, in tubes, which were not very confining at all. Yeah. So basically, you can think of them as basically being not there. But once, and that's something we want to study now, once you confine the system a lot, you should see changes to your dynamics. Yeah. And yeah, so the interactions so far in the regime that we looked at were weak. If we make the decay slower, the time scale due to interactions becomes kind of important. And then what you see is that your decay behavior changes completely. And then if you go to a limit where the interactions are completely dominant, yeah, you get completely different behavior. So the question is always like, what's actually the interest of what you're doing? Yeah? And so here we wanted to sort of make connection to what happens in photonic system. But I know that photonic people in waveguide QED, they are now looking at what happens once I have nonlinearities in my waveguide. And so that's something, of course, we can easily model or easily create.
Many more, but just one last one. How do you model the non-Markovianity? Because you don't have JKLS, you don't have Lindblad. I mean, you could have Lindblad with negative gammas.
So actually, I mean, I would be very happy to put you in touch with Alfonso, yeah, regarding, he's just around the corner, so he could sort of, hold on. Yeah, so he solved this problem exactly. It's a mathematically exact solution, yeah, so no approximations whatsoever. So he found some symmetries, some underlying symmetries that he can sort of use to generate the solution without actually knowing the solution. And then sort of using, yeah, this is this mapping, you know, using these generalized symmetries to find a mathematically exact representation. He thinks it's basically the prescription that he followed, that he developed, can be scaled up to more than 2 emitters. Yeah. But of course, it's going to be very, very complicated to go to larger system sizes.
In the spontaneous decay experiment, my question is, why didn't the probability go decay to 0?
Very good question. That's actually, you have a very good eye. Yeah? So I glanced over this. At the time, this is actually the effect that the radiation in our system is not really able to escape. Yeah? But it's trapped in a tube. And we don't only have a single excitation, but there's many. They're just very spaced out. But basically, in the end, you get the reverse process taking over, and they have an equilibrium between emission and absorption. Yeah. And so we didn't see this here, yeah, but in other regimes, actually, we have to be very careful. This is a different effect, yeah. But you basically, what you can do is you can blow out the radiation that has been emitted through some other process, and then we see the decay to 0. So this is really an artifact of radiation getting stuck and not being able to escape.
Okay, thanks.
Okay, so thank you for a very interesting talk, and congratulations for the experimental results that you got. So I have 2 questions. One is very simple. How many atoms, how many wells you have in your experiment?
Okay, so we have about 1,000 tubes that are populated in parallel. And each tube has maybe 2 or 3 excitations in it, if they're very rarefied. Yeah. Now, if in a mod insulating regime, we have, of course, many tubes, yeah, that have one atom per side of a certain range. Yeah.
One atom per side.
One atom per side, roughly. Yeah.
And then a general question about the motivation. You said that this system provides an analog simulator for an optical system that is very tunable, and you can study the physics. Mm-hmm. But you cannot use it for direct technologies.
That's right. Yeah.
But can you get a feedback so that, let's say, optical system can be engineered in a way that from what you learn from it?
Yeah, I mean, look, we already had an example. For example, no one was able to observe these non-Markovian oscillations. And then 3 years later, they were observed in I think, a microwave, a transmon qubit setup, yeah? And so, I mean, ultimately, and I glanced over this too, yeah? In this motivation slide, I put this, yeah? So the question is, why would you want to simulate a system that itself is tunable? Yeah? And so, for example, the transmon setups are very tunable, yeah? And so, it's a fair question. Yeah? So why, ultimately, if the system that you're simulating is as simple as your system, why are you simulating it? Well, I mean, I think I gave the answers here. We can explore these effects very quickly and sort of get an understanding, and then they can use that and sort of make it technologically relevant. Of course, you could say, if you guys don't exist, they will do these studies maybe a few years later, but yeah. Okay. I mean, ultimately, I always think of this in terms of, there's a Hamiltonian there, yeah? We want to learn about this Hamiltonian. Who cares what system you use, as long as you study the Hamiltonian. And then the application, that's a completely different question.
Okay, thank you.
Okay, thank you. I think we can conclude this colloquium. Dominik will be here in the theoretical physics department, sitting there until Friday. So if you have more questions or want to talk to him, how to measure things, how to write a PhD thesis,
I would be happy to talk to anyone.
And I think we will continue with the colloquium series in February with some, I think, dark matter. Is that correct? Yeah. We'll see. So thank you again, Dominik. And
thank you.
To everybody, have a nice break until the next colloquium. Thank you.